So, lecture number 2. Yesterday I talked about toric varieties, but using quivers as a way in, as an example, as a way to give us a surjective map of Z modules that made it work. So, as a very brief reminder, so for a quiver Q, the driver for everything I was doing was the incidence map, whose image I called lambda. I guess Q was connected. And then inside here there was the sub-semi group that mapped down its image I called lambda plus. And I'm interested in slicing this semi-group to get a collection of lattice points that are the points in the convex hull or some convex polyhedron. And so the point then is that that's, if I have theta in lambda plus, then we get a toric variety. So x theta equals AQ1 double slash by a torus that I wrote down, determined by lambda. So that's the GIT quotient. Now, in light of Joshua's talk from this morning, I can say a little more. Right, so for theta in here, when theta is 0, this is exactly the affine GIT quotient that Josh was talking about. This is just spec of the invariant ring for the action of this reductive group, this torus. When theta's non-zero, so Josh also talked about the projective GIT quotient. Now, notice that my variety I'm taking quotient of is not projective, patently. So in fact, everything he said works for a variety that's quasi-projective. And so as a reminder, the point in his talk this morning was, if I've got something projective, I take an ample line bundle and embed it into a projective space. That's step 1. And then I choose a lift of the action of, in this case, the torus on our variety, so it acts on the ambient projective space. And he made reference to the choice of a character that one can introduce when doing that. Well, there aren't very many interesting line bundles on affine space. So I've only got the trivial bundle, but I do have the choice of character. And that is exactly what theta is. This is the group of characters of T, and so suddenly we're in exactly the world of projective GIT, as long as we can say quasi-projective GIT. So that's the setup. That's the general thing. And the other thing was, if I take theta in the movable cone, so in particular, and perhaps I'll intersect, let's take an integral point. So let's stay within lambda plus. So if assume that it lies inside a top dimensional cone, so in the interior of, and I called it the secondary fan, and that's the right word for this context, but I'll also call it the GIT fan. And again, in reference to Joshua's talk, insisting that it lies inside one of the top dimensional cones is equivalent to insisting that, and I've not talked about it very much, stability, but that's insisting that the notion of theta stability agrees with the notion of theta semi-stability. And that's the situation where Joshua told us we win. We win everything. And that gives us this nice assumption inside the top dimensional cone. So right at the end of the talk, I was a little bit rushed. I do apologize, so I didn't say it very well. So in general, our toric variety, if we're not dealing with quivers, I may have said it's Q factorial under these assumptions. Because I'm dealing with a quiver, I can actually say something a bit stronger. So one or two things are much simpler in the case where we're dealing with a quiver. Actually, another which is also, Michel asked about my polyhedron, whether it was a lattice polyhedron, and he's quite right that in general it's not. In the quiver case, it actually is a lattice polyhedron. So sorry about that yesterday. So for us, it's a lattice polyhedron. This is non-singular, and the Cox ring, and I think I didn't use the phrase, I didn't use that notation, but I defined it as for all elements in the class group, but my variety is non-singular, so that's the Picard group, and I add up, take the direct sum of the cohomologies, I think I want to call it L lambda, and at the end of last time I pointed out under these assumptions that our Picard group is isomorphic to lambda. That really is the secret. That's our Picard group sitting there. The observation from last time is that this is the graded ring that drove everything that I did yesterday. So So this is the ring I used all the time to give us everything, and then the point is that that gives us understanding of GIT quotients. But this observation, or this isomorphism, says it's intrinsic. That's the thing I want you to take away from the talk yesterday. The Cox ring is intrinsic to x theta, and it allows us to understand, so this is not, and the Cox ring encodes completely the birational geometry of this variety via rational maps. So from x theta, we have rational maps to our other GIT quotients, and now where lambda is in lambda plus. And if I'm in the interior of this thing, then they're birational. So I can probe the geometry. And I thought it was worth illustrating very clearly. There are two examples I was doing. One I did explicitly and one I left as a wee exercise. So the first quiver I wrote down was this. And so in lambda, our GIT fan, or our secondary fan, this is going on in lambda, and I guess I'm drawing pictures that look like they're in a vector space, so we might want to draw a picture over the reals. So this is our lambda plus, and I pointed out that in this example, the effective cone is the whole thing, the movable cone is just that. So there are 4 different types of quotient I can get, and so I was interested in particular in theta being 1, 1. For that lattice point, I made the point that our variety was F1, but if I move lambda around, so I move our parameter away from there, I get some other options. So when I move it to the point 1, 0 down here, it turns out there are 2 arrows in there, 2 maps from the origin to our 1, 0, and the toric variety we reconstruct there is P1, and sure enough, F1 is well known to be a P1 bundle over P1. When I move my parameter to this point, then I have an arrow going up, and I also have arrows from 1, 0 to 0, 1, and so I've actually got 3 paths from the origin to this point, one directly and a pair that pass through there. It turns out the space of sections of this line bundle is of dimension 3, and sure enough I get a morphism to P2, and then if I choose the origin I get a point. And so that picture tells you an awful lot about the birational geometry of the variety determined by a point inside one of the chambers. That's our x, this is the x theta I'm thinking about, and these are 3 different x lambdas. Since it's, I can't resist, and I think it's more important to do this one, just add 1 extra arrow in. So I suggested this is an example that's worth thinking about. Having put this in, our incidence map looks the same except there's 1 column that's repeated, the -1 vector. So this part looks the same, but I did draw for you that our lambda, our secondary fan looks like this. And now the movable cone is the whole thing. I have 2 top dimensional chambers which I might feed into this setup. And if you do the calculation, and I really urge you to do that, either for theta equals 1, 1, or perhaps up here, there's, let's call it a theta minus, equals -1, 2, will be inside this chamber. Calculate those lattice points in that slice. For each of these guys, there were just the number of lattice points there are 8 lattice points. These are lattice points in polytopes of dimension 3, and it's worth drawing. I practiced. It's a tent. So it's a 3-dimensional polytope. That's intending to show there are 6 lattice points in a plane at the bottom, and there are 2 that are higher up. So that's what one of our convex polytopes looks like. Let's say that's for theta minus. And then as I go across to theta plus, I also get 8 lattice points, but they're arranged differently. And that's why the calculation I went through yesterday for F1 is helpful. Having a collection of 8, and here's what they look like. Oh no. So again, I've got a plane with 6, but there's one there, one there. Perhaps I won't put that, maybe I'll put it there. Is that going to go well? That is also a tent. But the thing I want to draw your attention to is that the top of the tent are pointing in different directions. So the polytopes, I mean, the polytopes are actually isomorphic, right? You can rotate one to hit the other. But the directions of all these inward pointing normal vectors are important. In this information, I said this, that topologically you can understand the toric variety you get by looking at the polyhedron. And somehow the difference is that data up at the top, there's an edge in 2 lattice points. In terms of the decomposition into torus orbits, there's a C star and a pair of points. So there's a P1 there that when you actually pass into the middle, it disappears. I shan't draw this one as well, but at the point 0, 1, you have a square on the bottom and a single lattice point. And then across on the other side, that same P1 is coming here. So at least this is giving us a flop as we pass from this chamber back and forth to this chamber. So this is a rational map between 2 smooth projective threefolds. So the wonderful thing about toric geometry is that you can calculate everything and you can see some subtle phenomena even with some genuinely simple examples. So if you've not seen this before, please, I urge you to calculate those 2 polytopes. This is, N5 intersect inverse of the 2 different thetas and carry out calculation. Oh dear. Right. I didn't think I'd cover all that yesterday, but I thought that was worth doing. That's toric geometry. Done. Covered.
Sorry.
No apology necessary.
What is the secondary polytope in the secondary fan in the second example? Does it include that arrow in the middle or not?
Yes, so good. So the secondary fan, you take the positive quadrant up in N, in this case 5, map the whole thing down, so the support of the fan is just this much. But it's a fan, so it's a decomposition of codes. That arrow is in there, so there are 2. So the yellow bit I've drawn is the support of the fan, but it's a union of cones. So there are 2 different top-dimensional cones. So somehow the 2 varieties I get, one on each side, are equally good. I can use theta plus, perhaps, and theta minus. I can apply the theorem to both. They have the same Cox ring. So yeah, there are 2 top-dimensional chambers there, and you can choose either one. You can see there's enough symmetry in the situation that there's not that much difference between the 2. Right, so this is toric geometry. Fundamentally, I've got an affine space and I'm acting by a torus, and that's why we always stay in the toric world, because the affine space contains this dense torus orbit. Now I want to move, and I'm just going to add in one extra piece of information, a quiver with a dimension vector that I'll call V. It's a tuple of non-negative integers, 1 for every vertex. And so everything I was doing yesterday, I was implicitly dealing with the choice 1, 1, 1, 1, 1. So the point is that then for every arrow, I've got the tail, the arrow passing to the head of the arrow, and now what I'm going to do is I'm going to place a vector space of the appropriate dimension on each vertex. So, and I should have said, one of my friends pointed out, I didn't say K was a field. I do apologize yesterday. That's my font for a field. So the vertex is indexed by the tail, so it's V indexed by the tail of A, mapping to K of V indexed at the head. So yesterday, Z sub A's were scalars, and now they're matrices. So so each of these, for every arrow, I have V head of A cross V tail of A with coefficients in K matrix. So the assignment for to every vertex, a vector space of dimension vi, and to every arrow, a linear map between the corresponding vector spaces is called a representation of the quiver of this dimension vector. And I'm going to build the analog of our AQ1, and I'll call it rep Q of V, but this is playing exactly the same role as AQ1 did yesterday. I just build for us a great big vector space comprising one matrix for every arrow in our quiver. Now, this looks very like AQ1 except it's a higher dimension, but the bit difference comes now. So this admits an action. So now I've got vector spaces of dimension vi on each vertex. So rather than having our torus that was a product of k stars and crucially GL1s, I now let GLVI act at each of those vertices. And this is by conjugate, so by change of basis. If I have a tuple of elements of GL acting on this collection of matrices, then it's exactly as we teach to our linear algebra students, where we do change of basis on each of the vector spaces. So it's the group action that's more interesting, that's less toric. Just to make my life easier, and it doesn't actually change anything, but it helps me, I'd like to make a mild simplification, and it's not a bad place to start. My dimension vector, I'm going to ask that one of its components is 1. So suppose, I'll just assume for the rest of the talk, there exists a vertex. I'll call the vertex 0 out of habit, for which v sub 0 equals 1. The benefit of doing this, so the point is that this group doesn't act faithfully on this space. But if I'm armed with this assumption, so I really should mod out by a diagonal copy of GL1, but by introducing this assumption and by breaking the symmetry, then I can just let the group I'm going to be working with is the product of GLVIs at the non-zero vertices, so all the other vertices. This is isomorphic to the action of the quotient of this by a GL1, so this acts faithfully on rep QV. Right, so on with this then, the key definition, and it simply generalizes everything that I was saying yesterday for any theta in lambda, which I'll define to be the group of characters of G. Well, each GL introduces a copy of Z, so this is isomorphic to Z rho, for rho equals the number of vertices minus 1. So I take any character and I define the GIT quotient as follows. So for theta, so x theta, my GIT quotient, I take this vector space and I take the GIT quotient with a choice of linearization theta. So the definition I gave you yesterday, this is proj of the graded ring. So I take the coordinate ring of the variety on which we're acting, and then for my theta, I take all the graded slices for j greater than or equal to 0. Same definition as yesterday, except rep and g looks slightly different. So that's our GIT quotient, and this is, just as yesterday, this is projective over the affine GIT quotient. X naught, which is spec of the ring of invariance. Okay, Okay, and so in examples, I think I'll always be working with quivers where the ring of invariance is just the field K, so the varieties I'll be looking at will all be projective varieties. Okay, so these are called, well, these are examples of quiver moduli spaces, but before I say more about that, I want to do an example because let's do the natural non-toric example. So what are we gaining? And the example's very simple and very natural. So I take two vertices and n arrows for some n. And the dimension vector, which I also have to choose, I'd like to put dimension 1 on 0 and dimension r on the second guy. And I'm going to assume r is less than n. Right, so I've got a collection of arrows. The representation space should be a direct sum over all arrows, but each one is a column vector, and I'm just going to gather them together into a single matrix. So n column vectors, it's just a matrix, the collection of r by n matrices. And our group G that acts is just, it's only one copy of, the GL1 isn't there, it's just GLR. So G equals GLR acts. And in fact, it acts in such a way that we have this ring just to be the field. Right, so it's not hard to see that with the invariance, spec of the ring of invariance is just a point. So our affine GIT quotient is, I think we can agree, deeply uninteresting. So now I'd really like to, so it's great, Joshua's been, the thesis, part of his point of view in his talks is that computing invariance is hard. And this is exactly, of course, what I'm trying to do. Right? I did it in the toric case for the F1 and showed it can be done, but it's complicated even in simple examples. I'd also like to do it here. When it's a torus, it's more tractable. When it's GL, it's of course much harder. So I'm going to use, so GL contains SL, and the quotient is a one-dimensional torus that I'll call T. Couldn't work out whether it's right 1 or 0 at either end. So I've gone with 1. So what's the point? So we know that GLR has character group the integers, and so does the torus. So these groups have the same characters, and perhaps I'll draw it in the other way. So G check is isomorphic to T check, which is just the integers. Okay. Right. The key point, and this I hope helps to. Question?
May I ask, in this mild simplification above, do you assume that the quiver is connected also?
Yeah, I guess all the way through. I mean, yeah.
Okay.
Shall I do that? Yeah, I guess implicitly, although I accept this was the toric situation, I was assuming that's surjective. So yes, thank you. The quiver will always be connected. Yeah, thank you. Right. I'm trying to work with the definition project of the graded ring. I want to understand functions that transform under the character theta for some choice of character in G. So I'd like to understand things that lie in here that transform under some character theta, and I'll deliberately point at that. So assume for the moment that's a character of G. So this is true if and only if, firstly, so we're sort of decomposing the problem into two pieces. Firstly, that our function is SL invariant, so that's one thing we require. And the second thing I require is that it transforms according to theta. So it's theta semi-invariant, where I could give this isomorphism a name. If you don't mind, I'm not going to, but I'll say I now regard theta as a character of the residual torus, right? The residual torus acts on this ring. So I want f, so I'm breaking the problem down, I'm tackling this not head on, I'm dividing up the problem. The point is, this ring is something that we know something about. So SL invariance for this action for the SLR action. Did I say SL? Right, I'll call it SLR, sorry. SL comes later. Right, so this ring is generated by determinants of maximal minors. Right, so to be invariant under SLR, one way I cook up my matrix of scalars here, but I can populate the same matrix with the variables of this polynomial ring. Then I can compute the appropriate minors, and indeed we're exactly computing the Plucker coordinates. And so some determinant of a maximal minor is non-zero on some B, some point in our representation space, if and only if the corresponding point, when viewed as a map from Kn to Kr, or if you like, the matrix has maximal rank. So this is surjective. But I go back to my first description of Proj of the graded ring the other day, yesterday, that to work out what I want to choose generators of this ring, and then when I do the construction, and this is really getting towards the semi-stable locus, so rep of QV, and I took the semi-stable locus, and then I was taking quotients by G, and I said this is exactly the collection of points in the complement of the zero locus of generators. So I'm interested in only the points that survive, the points that remain semi-stable. In fact, this is equivalent to theta stable. So let's assume theta equals +1 for the moment. So I'm only interested in points for which none of these generators here vanish. In other words, the only points that are semi-stable are the maps that are surjective. That is, x theta for theta equals 1 parameterizes the collection of such surjective maps, but then modulo the action, perhaps I'll write it this way, it's the collection of B's from Kn to Kr that are surjective, but then I modulo the action of GLR on the target. This is exactly the Grassmannian of quotients. So for me, I'll write it this way. This is the Grassmannian of, right, so of course people would naturally like to think about the Grassmannian as subspaces of dimension n minus r in a fixed n-dimensional vector space. I prefer the quotients, so I'll use the notation n semicolon r as a reminder that r is the dimension I'm parameterizing quotients, not subs. So for theta equals +1, this quiver gives us the Grassmannian. For theta equals 0, I've already told you what it is. So x naught is a speck of just a point. And the point is it's empty otherwise. So, where did I see? Yeah, so x naught is here, and then it's empty otherwise. So x minus 1 is empty. And so now you can actually see the GIT fan happening here. So it's the place where theta lives. So this is in lambda, which is isomorphic to the integers. And the movable cone, which is the Neff cone of our Grassmannian, is exactly this piece. And of course there are three different quotients. The Grassmannian is one option. There's the point, and then it's empty. And this is really quite familiar from this sort of setup. I had some given variety. As I moved through the origin, I got a point, and when I went beyond it, I had nothing at all. My quotient was empty, so I didn't even think about it. That's an example of a quiver variety, or one of these quiver moduli spaces, that is not toric. Okay, any questions at this point? This is kind of key. So it's a rare situation where we can actually compute everything just using invariance. So I used the word, yeah, Richard.
In this particular example, you have a GLN action as well. But that is not covered by your theory, right?
Correct. I'm not using the GLN. Oh, the only GLs that are acting are those of GLVIs. Yep. Okay, a key observation here is that the Grassmannian is more than just a variety, right? So Gr of NR carries a tautological morphism of vector bundles. So I take the trivial bundle of rank n and I have a surjective map to some vector bundle V whose rank is R. The point is such that the fibre over any point where the fibre over any point of the Grassmannian is the corresponding surjective map that gave birth to the point in the first place. So it's a fine moduli space. Actually, I'm not quite sure where I put it in brackets. I'm trying to emphasize this point. It's a fine moduli space. So the same is true much more generally. And this is, and I've got a theorem, and I'm attributing it to Alastair King, who's a colleague of mine, but that's probably a bit generous. So I'll call it GIT and King. So some of it's Alastair, but much of it is, of course, general GIT. Oh, and I'm aware I shouldn't go too far down. So some of this is general, and it's exactly some of what Joshua told us this morning and yesterday. And he made the point, right? So GIT quotients are a way of constructing some moduli spaces. Well, they are the way of constructing these moduli spaces. I should say, I've chosen theta stability and theta semi-stability are for me sort of implicit. It's interesting that Joshua and I, without having talked about it, are deliberately taking completely different points of view. I've chosen not to talk about stability and semi-stability for perverse reasons, partly to show what one can do, but he's quite right that it's a really stupid thing to try to do because it's difficult. So the theorem is, suppose, in general, for our quiver setup, as in the definition, theta in here, so I've got a choice of character, lies inside a top dimensional cone of, so the GIT fan. So this is the analogue of our secondary fan, and in fact, this is a wall and chamber decomposition, the decomposition that Sohaila talked about on Monday with a much more complicated gadget. So this is a finite polyhedral setup. So then, I'm adding in the assumption that it's in a top dimensional cone to get a stronger conclusion, and the stronger conclusion is that the map pi from the representation space, I'll say theta semi-stable, because I effectively gave the definition yesterday and I've been implicitly using it here to talk about this setup. It turns out, by this assumption, this is the same as the theta stable locus. So when I'm inside a top dimensional chamber, they agree. So I have my map. This is a geometric quotient. So I'm parametrizing orbits, just as is a geometric quotient, as Joshua told us. And then, crucially, so there are two assumptions I need, and one of which I've got for free by my simplifying assumption. So I want my vector to have a component that's 1. More generally, if I don't add the simplifying assumption there, I need to assume that my dimension vector is indivisible, so not a multiple of some other integer vector. But I get that for free. So x theta is a fine moduli space. And I'll put theta stable in brackets just because I didn't define it explicitly, representations of the quiver of dimension V. But what this really means, so it comes equipped just as the Grassmannian in that case, with two pieces of data, and I'm conscious that maybe I'll leave, perhaps I won't go any lower, right? Is that? I'll leave that there. So two pieces of data, just as with the Grassmannian. So a collection of vector bundles. Do I want that? No. But also morphisms between them. So it comes equipped with a tautological vector bundle, locally free sheaf, so vector bundle, and I'll call it, so there's, for every vertex, I have a vector bundle VI with, so V0 is, I'm going to assume is the trivial bundle. And if, oops, m theta, sorry, that's a habit of a lifetime, x theta. So my simplifying assumption tells us, so I'll say each of these has rank equal to VI. And so the rank of VI, that's curly V, equals straight V. That's part of our dimension vector. So in general, the ranks of the tautological bundles on here are exactly the dimensions of the vector spaces that sit at every vertex. Indeed, as we move around this space, I'm parameterizing representations of a quiver, and the tautological vector bundle is exactly singling out this vector space in each of our representations. And so because of this simplification, I have one of my bundles is going to be rank 1, and I should say more generally, if you don't add this assumption, then there's I'm making a bit of a choice here in assuming it's the trivial bundle. The point is it's the relative HOMs between the bundles that are the key things. So there's some normalization that I just have to fix, and I've decided to fix it by insisting one of them is the trivial line bundle. So I got a tautological vector bundle, and secondly, for every arrow, I get a morphism from V at the tail to V at the head. So perhaps said more properly, I've not said anything about the path algebra of the quiver, but there's actually, I'll write it. There's a K-algebra homomorphism from the path algebra of the quiver to the endomorphism algebra of the whole bundle itself. So K-algebra. I don't want to say any more about that, but that's the tautological information you actually get. Tautological vector bundles and a tautological homomorphism. It's simply encoding some morphisms between the bundles.
Ask your question.
Yeah, fire away.
What are these maps in the case of the Grassmannian?
So I was going to do F1 to start with, but it's exactly the n different maps that you can see there. It's exactly that. So the only thing is that I've broken apart, by smushing, by smushing all the arrows together into one matrix from here to there. Yeah, okay, good. But so I'll show you F1. So as an example, when I draw the quiver like this, and that looks like combinatorial data, what I see is I see the trivial bundle from and I'm choosing theta equals 1, 1. And I remind you, so in the case I was doing yesterday, my dimension vector is always 1, every one at every vertex. So for this vertex, by my assumption, I've put O there. At the second vertex, at the vertex that I've called number 1, I have some line bundle, I'll call it O of 1, 0, that's sort of where I placed it. But what we're actually seeing here maps from, the arrows are showing me a basis for the space of HOM. So the arrows from 0 to 1, if you think of what's happening here, it's the space of HOMs from O to our line bundle. Well, these two arrows are indicating I've got a two-dimensional vector space. In this example, this is an isomorphism, actually. but one doesn't always have that. So whatever line bundle I've got here, it's got a space of sections in dimension 2, so I'm getting a morphism from F1 to P1. And that's exactly what this line bundle is. And up here, again, I've got 3 HOMs from here to here, 1 that goes that way and 2 that pass through this way. And I have the line bundle, OF1, that one might call it 01, but that's the globally generated line bundle that gives the morphism to P2. So F1 is the 1-point blow up of P2. And indeed, so when I look at this quiver, I see this. So some of the key take-home, if you've not seen these quiver GIT quotients before, that yes, quiver varieties, moduli spaces of quiver representations, they are GIT quotients. So they are varieties, but they come together with a choice of a privileged collection of vector bundles and morphisms between them. And so this is actually why when Alastair King introduced these things, one of the first things he thought about was derived categories of toric varieties in trying to produce certain vector bundles, or in that case line bundles, to try and generate the derived category. It's exactly because with a quiver construction you get a preferred collection, or you get a collection of line bundles, and if you've chosen wisely, then they may tell you some deep geometric information. And the one other example, just to generalize the Grassmannian, I'll just write this very briefly, is the flag variety of type A. So if I put n arrows in here, just as in the case of the Grassmannian, but then I put a single arrow, let's choose row vertices, a single arrow everywhere else, and I choose the dimension vector v equals, well, still 1 at the tail, but I put, let's just list them, v1, v2 up to v row, where I still insist that the dimension here is less than n. I now insist this is greater than v2 and so on. So that's the requirement I'm putting on this dimension vector. Then if I choose theta to be +1, perhaps I've been drawing my thetas as column vectors, so I'll do the same thing in this lambda. It turns out that for this quiver there is only one top dimensional cone in the GIT fan. So I'm just picking anything in the interior of that top dimensional cone. Then x theta is isomorphic to, it's a similar setup, it's linear maps, and the choice of stability condition is insisting that each of the maps is surjective. So it's the flag variety, partial flag variety. Again, I'll use semicolons to remind you that we're dealing with quotients. These are all, the maps are all surjective. So partial flag variety of type A, just from this quiver. Okay. My title, which it's still up there, up at the top, Cox rings. I've taken this approach because I want to talk about the driver in the toric case was the Cox ring. It was intrinsic, and it allowed us, when we do the calculation of all of these different polytopes, to probe and really understand completely the birational geometry of the toric variety. So I'd like to understand what the Cox ring is, and if it's a nice ring, does it have nice properties, and can one make a similar statement having boosted the dimension vector away from just the 1-1-1 case. And so the definition of, so this is terminology really. So definition, I'm going to call, have I assumed yet that no I haven't, right, so I'm going to call x theta a quiver flag variety if Q, the quiver that is connected, I want it to be acyclic, so no non-trivial cycles. If the Q is acyclic with a unique source vertex. And that's the case for all the quivers you've seen so far. And in fact, I want to choose the source vertex and I want to call it 0, the same one that I gave dimension vector 1 to this point, which I just wrote there. Same vertex 0 with, and I'm going to assume V0 is 1. And moreover, and this is a little harder to motivate, so theta, I want it to lie in. Now, the movable cone, which is a cone sitting inside the corresponding vector space, just as when we played with the secondary fan, so theta lies inside a top dimensional GIT cone. But this statement, this bit here, is actually equivalent to a statement about the Picard group of x theta. So I'll write this statement down so then at least you can see why I'm adding this assumption. Well, you know why I like to be inside a top dimensional cone? Because I like to win when theta stability equals theta semi-stability. But the proposition is this. I've chosen to enumerate my vertices, and that feels offensive to me. So I'm not going to enumerate my vertices. Sorry. So there is an isomorphism. An isomorphism of Z modules. So rho. Where has rho gone? Rho was the number of vertices minus 1. Still visible? Probably not. Okay, so I won't enumerate it, but let me remind you and me that's the number of vertices minus 1. So there's an isomorphism from Z to the rho to the Picard group of a GI of a quiver flag variety. So let's assume X. So I'll better say for a quiver flag variety. For any quiver flag variety. And this really is why I'm putting in this assumption at the bottom. If I move out of the movable cone, then I lose the isomorphism. And it's exactly like the example I did with in F1. F1 is an example of this, where I was saying, this is effectively a picture of the movable, I've read this off as well. The movable cone is the positive quadrant in this case, and there's other stuff over here. F1 has Picard rank 2. When I move over here, my GAT quotient is P2, and my Picard group has dropped down to rank 1. So I don't like that chamber, I do like this. That's why I'm insisting on movable cone. So the point is I get the Picard group of the rank I expect, where, what is the isomorphism? I take a tuple, L1 through L rho, and I send this to the tensor product of. Now, I've got all these vector bundles VI. Their determinants are line bundles. So this is it's a bundle of rank R. This is the rth wedge of that rank R bundle is a line bundle, and I use these lambdas to be the exponents on these, and then I take the tensor product over everything inside. Okay, now I know why I enumerated my vertices. Sorry about that. So if this is a lambda, my lambda is a tuple, I'll call this line bundle L lambda. So that's an isomorphism. That's describing what the Picard group is. So these vector bundles are giving me all the information about my Picard group. In fact, one can say much more. You can boost this up to a statement to say that these vector bundles in this context, if you take certain Schur powers of them and tensor them together, you can actually get a tilting bundle on these varieties. So again, related to Sohaila's talk, there's a full, strong, exceptional collection of vector bundles on these varieties, or if you like, the bounded derived category of coherent sheaves on any of one of these things is equivalent to the derived category of modules over the endomorphism algebra of that great big direct sum of bundles. But so these, this is just generalizing the theorem of Kapranov for the partial flag variety, and also for the Grassmanni and valence. So there's that sort of statement, but this is a weak avatar of that. But such that the movable cone, now I have been talking about the movable cone as if it's sitting in lambda. This is lambda, I remember. So I've been using the phrase, the effective cone and the movable cone sit in the space of GIT parameters. Well, in fact, the movable, so I was asked yesterday, why do I call it the movable cone? And I said the divisors inside the, or line bundles inside the movable cone are movable. They have no fixed component. So I answered the question by talking about the movable cone in here. I'm giving you a cone that I'm calling the movable cone in here. The point is that the thing I'm calling MOV is identified with the movable cone under this isomorphism, right? Where, and I'm not quite sure how to write that, where our MOV is identified with the movable cone in the sense of geometry, the movable cone, but and the GIT cone containing whatever our theta is, which lies in the movable cone, that GIT cone, and in particular the characters in it, is identified with the collection of all ample line bundles. So identified with the ample cone of our GIT quotient. Put simply, the decomposition of the GIT fan is giving us all the information we care about the way line bundles encode interesting geometric information in the Picard group. Okay, so now I can make the final statement. I'm interested in the Cox ring, so recall the definition that I think isn't there. So recall, so the Cox ring, at least in this context, let me define it to be a direct sum over all line bundles, and they're all of this form L lambda, of the space of sections of that line bundle. So I'd like to say something about this ring and relate it to the first talk, and indeed, crucially, to the example of the Grassmannian. And so I'd like to define, to make the final statement, let me introduce the group SL to just be the product of all the SL VRs. So I in Q naught. So actually I can improve on this a little bit. So remember, I'm assuming that V naught is equal to 1. And so this guy sits inside the product of all the GLs, but of course GL of V naught is case, so SL of V naught is trivial, right? So in fact, I've said I in Q naught, but I can equally well say I is not the zero vertex because I'm dealing with GL1 there. So for this group, this guy embeds into our group G, and let me remind you, this is the product of GLs, I non-zero, and this maps to a quotient torus, which now is isomorphic to K star to the number of vertices minus 1, which is this integer rho. And so the main theorem says, and it builds on this Grassmannian case, and this is why I did the Grassmannian this way, by invoking this short exact sequence, because it's a special case of a more general statement about the Cox ring of these quiver flag varieties. And so the statement is that the Cox ring is isomorphic to the semi-invariant ring. So, theorem, the Cox ring of a quiver flag variety x theta, and we do have some assumptions on here. It's not just any old quotient of rep q by this group G. I am working under these assumptions, so it's acyclic with a unique source, and I'm not choosing any old theta. The Cox ring is isomorphic as a Z rho graded ring to the SL invariant subring of our coordinate ring of the representation space. And so to be clear, SL, if it's acted and I've got this fixed locus, then there's a residual action by T, And I said yesterday that having an action by a torus is equivalent to a grading by the character group of the torus. And that's exactly why this is Z rho graded. Remember, Z rho equals lambda, which is the character torus of the character group of our torus T. And so now let me quote Josh again by pointing. So this is he said SL is a reductive group, and products of reductive groups are reductive. And this is the invariant locus for the action of a reductive group. And this was nothing more than a polynomial ring in some collection of variables indexed by the number of arrows. And so, as a corollary, some of the point of this is that this is finitely generated. So hence, Cox of the quiver flag variety is a finitely generated K-algebra. And so Hu and Kiel would tell us that x theta is a Māori Dream Space. And so these lectures have sneakily been intending to sort of introduce you to Māori Dream Spaces without giving you the word until the final couple of moments. Māori Dream Spaces are spaces for which Māori's program works optimally. So what do I mean by this? Well, of course, I urge you to go and have a look at Hu Kiel's paper from 2000. But what this says in particular is that for all characters of our, so lambdas, I should say, I mean, there's an isomorphism from lambda. I think lambda I defined to be the character group of G. But, so there's an isomorphism here. So for all characters, and this is isomorphic to pick of x theta, we have rational maps. So from our quiver flag variety, as I move lambda around, possibly in the movable code inside it, so I get birational maps. If I move to the boundary, I might drop dimension and get some sort of Māori fiber space. So I vary this, and x lambda is exactly, so a GIT quotient of this space is exactly taking the GIT quotient of our ring, Cox theta, by 4, and our appropriate lambda by t. But the point is that this is isomorphic. For our choice of lambda. So as I move lambda around exactly as in the toric case, I can investigate flips, flops, all sorts of Māori contractions. And I should of course say, sorry, it was implicit, I said there was one GIT chamber in this case, that the GIT chamber decomposition is just the positive ortho. There is one top dimensional cone here. It is the effective cone of the partial flag variety. And so one can have morphisms from the flag variety, but the birational geometry isn't interesting. It gets much more interesting in general. So these quiver flag varieties are Māori Dream Spaces, and in the special case where V is 1, 1, 1, 1, we're just probing toric varieties. Okay, I'll stop there. Thank you.
Very much. Are there any questions you can read?
Could you repeat what's the GIT fund?
Yeah, so I didn't define it explicitly for you. So in the space of all stability conditions, and this is true for the projected GIT setup by Michael Thaddeus on the one hand and Dolgachev Hu on the other, you've got some choice of linearization, but for me that's just a character. That's just a choice of a theta. So when I get a non-empty GIT quotient, I get some lattice point in a particular cone, and as I move that theta around, then the collection of points that are semi-stable or stable may change. And as I move theta around, if I'm inside one of these top dimensional chambers in the GIT fan, the notions of theta stability and theta semi-stability agree. But the moment that I move my theta so that a particular point somewhere becomes strictly semi-stable, then I've left this open cone and I move into a wall. And it's a polyhedral chamber decomposition. And so, yeah, the classic thing I like to draw a lot, one setup that naturally arises, vial chamber decompositions when you're looking at resolutions of ADE singularities, that if you're choosing a theta in a top dimensional cone, when you move it, if at some point and here to work out the inequalities, and here's where I really should be talking about the Hilbert-Mumford criteria, to work out what these what the walls are, they are telling me, just as Josh has taught us, which points become strictly semi-stable. And so when a point becomes strictly semi-stable, suddenly that defines for me a wall or a face of higher codimension. And as I keep on pushing through, then other points, for a theta prime on the other side, other points may be theta prime stable, and I'm exactly changing loci. So the lovely thing, oh, it's gone. The threefold example, the flops, I urge you to play with that and write down the setup and look at the theta stable locus and see how it works. So that's sort of a little bit about the GIT fan, but feel free to ask me more afterwards if you wanted to know something different. Rachel?
I'm curious for your proposition on this top middle word.
Yeah.
What of your assumptions about being a quiver flag variety are essential to that proposition?
So, excellent. So a quiver flag variety, so in fact the original definition of a quiver flag variety is so that theta is 1, 1, 1, 1. For that particular theta, if I send some of the coordinates, a sync in our quiver, if I send it from 1 to 0, I'm actually inducing a morphism exactly like in this flag. So for that particular theta, let's put it another way, the GIT chamber containing that has a supporting hyperplane where I can induce a contraction with fibers that are Grassmannian. So I get an iterative tower of Grassmann bundles. The way to prove this setup, so the way to prove this isomer, or the way to prove for that particular parameter, is to write down a tower of Grassmannians and point out that all the tautological vector bundles on the variety are pulled back from these tautological quotient bundles on all the different Grassmannians. And moreover, the Grassmannians have Picard group rank 1 determined by the determinant of that vector bundle, and that pulls back and does this. But perhaps more generally, it's very natural to say you can write sort of a map down. What's not clear in general is that it's surjective. So on a GIT quotient in general, I think it's an interesting question. When do we know that every line bundle is obtained by descent? So another way to think about this map is lambda determines for me a character of G. So up on the theta stable locus, I've got the trivial line bundle, but I tensor by the character, let's call it lambda. That descends to give me a line bundle on the quotient. That's actually what this map is. It turns out that in this context, this is a surjective map, but in general, I'd love to know, if I have a GIT quotient, when do we know that the Picard group is generated by line bundles coming from descent? And I actually don't know. So I'm giving a sort of I'm unsatisfied by my understanding at this point, but that's certainly what I'm using to get this. In general, the only nice context where one can prove something like this, if there's a tilting bundle, I can say something about this, and there is in this context. But yeah, that's where this is coming from.
Can you clarify what you mean MOV is identified with the movement?
Yeah, sorry, you can see I'm fudging here, right? So what I should do, I shan't write, but I'll talk more honestly. So in here, let's define a line bundle to be movable if it has no fixed part. So if you look at the space of sections, every effective divisor that's for which the line bundle is OX of D, if they all have to include a given divisor, and the classic example is F. All the sections of the line bundle that sits over here, O of -1, 1, sorry, I said I wouldn't write anything, have to contain that divisor. So it's movable when you have no fixed part. That determines some collection of line bundles in here, and generally whose closure is referred to. Some people call the cone generated by those. It turns out for Māori Dream Spaces, it's a closed cone. The closure of that cone is the cone I care about. So that gives a cone of well-defined line bundles over here, and that is identified with some part of the GIT fan. In fact, it's the union of closures of a collection of top-dimensional cones. So were I to live my life again, I might use a different name for that. And this theorem would say, hey, this cone that we were interested in is actually isomorphic to the movable cone and reserve the word movable just for the geometric thing. Yeah, thank you for asking that. It allowed me to be honest.
Was there any questions from Bidan?
Something that confuses me on the difference between character and line bundle is that it seems that in some cases where there is, character and linearization, is that in some cases where there's not really a choice for the linearization. For instance, if the Picard rank is 1, or if
So here, yes, since the GIT fan is a fan, the moment I pick +1, +2 is just the second Veronese of that. So you're right, as long as I only had to pick 3 characters, -1, 0, and +1, to probe all infinitely many possibilities. So in that sense, there is a choice, but I claim there's only really 3.
It looks like characters give you more choices, right?
Say again?
It looks like characters give you more choices, or is this not the... So character and linearization, understood as a line bundle, an ample line bundle, are not equivalent.
Oh, but bear in mind that I'm taking quotients of an affine space, and there's only the trivial bundle up to isomorphism. That's the only thing I've got. So I don't have any choice on the line bundle, but I do have a choice.
In the projective case...
In the projective case, then, it's yeah, you get much more choice.
And the other thing is, it's not fair to ask you, but Joshua is not here. So at some point he said that, how did he say? He said that in good choices of linearization, stable and semi-stable coincide, right? But
you can ask me that, yep.
Take, for instance, product of P1s, points in product of P1s, right? So you have a lot of linearizations you choose. And I mean, I'm almost certain that in all of them, stable and semi-stable don't coincide.
So your GIT fan in general,
I didn't understand the statement.
I've deliberately not said too much about the GIT fan, in part because I was sort of trying to keep away from stability and semi-stability explicitly, with hindsight leaving that unbeknownst to me, I was leaving that to Joshua, so that I could talk about invariance. But were I to talk about it, I would define theta stability and theta semi-stability in the sense of King. I would look at the vector space of all possible thetas and say, effectively the Hilbert-Mumford criteria, we test every single representation of a quiver and look for sub-representations that have some inequality that's greater than or equal to 0 or strictly greater than 0. And then I get if it's true that for every representation, then something is theta stable, if and only if it's theta semi-stable. I call that stability condition generic, and then I'm inside a top-dimensional cone in the GIT fan. And otherwise, then, you know, if the notions, if you have a theta and theta prime, if they, whatever they are, if they determine the same notion of theta semi-stability, then they lie in the relative interior of the same cone in the GIT fan. So there is a way to define the whole GIT fan explicitly. I left it a little bit implicit, but having drawn a few pictures in the toric case and say that you can write down the cone just by the image of the incidence map from the positive orthogonal and taking this common refinement of all the faces. So in this case, in the toric case, it's quite easy to write down what it is. More generally, it's really hard to calculate.